One type of reaction we have is called a redox reaction. Redox reactions involve the transfer of electrons from one species to another. To be able to understand redox reactions, we need to be able to understand oxidation states. An oxidation state is a number that has been assigned to an element in a reaction. So every element is assigned a different number. And there are a set of rules here, of course. But the numbers that we assign are called the oxidation state of that species. This allows us to determine the electron flow in a redox reaction. So it allows us to determine if the electrons flowed from something or to something. I want to be clear here, oxidation states are not ion charges. They often match, but they are not the same thing. It is coincidental if they are showing up as the same number, okay? Oxidation states are imaginary numbers that we use to track electrons within a reaction. Ion charges are real, measurable charges. So they are different things. Oxidation is defined as the loss of electron. Reduction is defined as the gaining of electron. So if a species loses electrons within a reaction, it has been oxidized. If a species gains electrons during a reaction, it has been reduced. Two mnemonics here can help you remember this. You've got Leo the lion goes grr or oil rig. Leo the lion stands for loss of electrons is oxidation, gain of electrons is reduction. So Leo, loss of electrons, oxidation, the lion goes, and Gur, gain of electrons is reduction. The other one is oil rig. Oxidation is loss of electrons, reduction is gain of electrons. Some students prefer one over the other. Pick one and use it. Okay, I don't care which one, but pick one. Oil rig, the only thing you have to remember is that you're only gaining or losing electrons, but that is true for everything we're learning. We only gain or lose protons if you're in the world of nuclear chemistry, and we're not covering that this semester. Oxidizing agents are substances that oxidize another species. They do this by being reduced themselves. So it's like a real estate agent. A real estate agent is not going to sell themselves the house, they're going to sell it to you. Okay, so an oxidizing agent oxidizes another species. It causes a different species to lose electrons by gaining those electrons itself. A reducing agent is a substance that reduces another species. It causes another species to gain electrons by giving up the electrons itself, by being oxidized itself. So our rules covering oxidation numbers. The easiest way to approach oxidation reduction reactions is by focusing on the oxidation state of each element in the reaction. We do have a set of 4 rules that we're going to follow to go through these. First, the oxidation number of an element in its neutral elemental form is 0. So what do I mean by that? I mean any element in its most elemental form is going to be 0. You can see Cl2 here. Cl2 is one of your diatomics. Oxidation number is 0. O2 is a diatomic as well, 0. Fe solid, iron in the solid form, 0. It's its most stable state. Carbon graphite, 0. Okay, these are all the most stable states of these species. Rule number 2, the oxidation number of a monatomic ion. Monatomic means one single atom, but it's in the ionic form, so cation or anion, is the same as its ionic charge. So, what is the oxidation state of each element in the following substances? I have to think about how these things break apart, and I think back to when I was doing naming. How do these break apart? Well, and I'm going to zoom in here just so I can write on the screen a little bit better. But if I looked at this, I've got Al2O3. That means I've got 2 aluminum 3 pluses and 3 O2 minuses. But that means my aluminum has a +3 charge and my oxygen has a -2. Notice I'm not saying overall, I'm saying that each aluminum here has a +3 charge. Each oxygen here has a -2 charge. For Fe2O, iron has a variable oxidation number or variable charge state. It can form 2 different ions, but I know oxygen is always -2. Therefore, my iron here has to be +2. Over here for Fe2O3, I've got 2 irons and 2 oxygen, or sorry, 3 oxygen. I know each oxygen has to be a -2 charge. Okay. Another way to do this is doing algebraically. I have 2 Fe's plus 3 O's that have to equal up to 0. I'm definitely not gonna have enough room to write this right there. So we're gonna move that up a little bit. I know that my oxygens are all a -2 charge. So 2 Fe's has to be equal to has to equal to +6, because this becomes, I'm sorry, there's no room in here. 3 times -2 gives me a -6. So when I add it to this side to get a +6, that means each Fe is a +3. Okay, so you can do it algebraically as well. If you need to see that, come see me for help. But I have 3 oxygens. Each oxygen is a -2. So overall, the compound is a -6 charge from oxygen, which means that the compound has to be +6 from the iron. I have 2 of them, so each iron would be a +3 charge. So iron +3, oxygen -2. Sodium sulfide. Again, sodium really wants to always be a +1 charge. Sulfur likes being a -2. I have 2 sodiums adding up to that. I have 2 sodiums at +1 charge each to counterbalance the 1 sulfur at the -2 charge. So again, let me just show you what I was trying to do. I'll do it with the aluminum oxide over here. So if I've got Al2O3, I know I've got 2 aluminums and 3 oxygens. And this has to equal out to a 0 charge because overall the compound is neutral. I know that oxygen wants to be a -2 charge. So my 2 aluminum plus my 3 times my -2 here. I know aluminum also has a fixed charge. We'll talk about that in a sec. This gives me an overall, let's see, plus a -6, which is the same as 2 aluminums -6. So 2 aluminums equal +6. Each aluminum is a +3. And I do the same thing with the iron 3 oxide, Fe2O3. So you can do it algebraically as well. The last one, these the sum of the oxidation states equals the overall charge. So if you've got a species that is charged, it does have to equal that overall charge. So for like H2O, H2O2, PCl3, PCl5, NO3 2, NO3, NO3 negative, and NO2 negative, we can see that we're going to have slightly different charges going here for the elements that we have. So let's look at each one. H2O. Hydrogen can only gain or lose 1 electron. It can't do anything else. It literally doesn't have the space to gain or lose more than 1 electron. But hydrogen would rather lose an electron than gain an electron. Oxygen would rather gain than lose. So the oxygen here is going to be a -2. The hydrogens will each be a +1, giving me an overall 0 charge. Now, when I look at peroxide, a lot of students want to tell me, well, oxygen's going to be -2. But here's the thing, it can't, because hydrogen only has 1 electron to give up. And I have 2 hydrogens, which means overall it can only give up 2 electrons. I have 2 oxygens. So here, the hydrogen will be +1 for each one of them, but each oxygen will only be a -1. So 2 times +1 plus 2 times -1 equals 0. 2 minus 2, giving me that overall 0. So here, oxygen is actually going to be a -1 charge. It doesn't have a choice. How about PCl3 versus PCl5? Chlorine likes to be a -1. It is a halogen. In order for that to happen, for this species to be neutral, this phosphorus must be a +3. I've got 1 phosphorus and 3 chlorines that have to equal 0. This is 3 times a -1. So phosphorus plus that 3 -1 equaling 0 means the phosphorus has to be a +3. We just decided that chlorine wants to be a -1, and it does. It's because it's a halogen. Halogens want to be a -1 charge. But that means for this species to be equal, this has to be a +5 charge. So I can see phosphorus can do +3 and +5. What about nitrate and nitrite? Here I've got oxygen, and oxygen, unless it can't, wants to be -2. There's a few exceptions. If you're in peroxide, it can't. And if you're paired up oxygen with a fluorine, the fluorine gets the negative charge. Most of the time, though, oxygen will get its way and be able to be a -2 charge. So I have 3 at a -2 charge, and this overall has to equal 1. So I've got nitrogen -6 equals a -1. Nitrogen has to be equal to +5. Because again, I have 3 oxygens there. In nitrite, the oxygen still wants to be that -2 charge. I have nitrogen -2 times -2 instead of 3 of them. It's still a -1 charge. Or sorry, nitrogen plus. So nitrogen -4 equals a -1 charge. Nitrogen overall will be a +3 charge. So instead of being +5 like it was in nitrate, it's now a +3 charge. There are some generalizations you can make here. First of all, metals can only be positive or zero. Everything can be zero, but metals can only lose electrons from their natural state, from their zero state, meaning that they can only form positive oxidation states or zero if nothing's happened to them. Nonmetals can have both positive or negative oxidation states and zero. The highest oxidation state an element can have is equal to the number of valence electrons that that species holds. So it is the old group number, but it's also equal. And I'll talk about the group numbers in a sec. But number of valence electrons. This one is the number of valence electrons -8. So the reason I say the old group number is some people, very, not as many now, but it used to be a lot more people teaching them that way. But the old group number used to be, if you looked at the periodic table, we're going to pretend that's a box and not so crooked. It used to go 1, 2, and then we would count 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Pretend those are spaced out. And then 13, 14, 15, 16, 17, and 18. So it used to be that the highest oxidation number it could have, or sorry, this is the current numbering system. This is what we call it now. We call it 1 through 18 now. What it used to do is it used to split these up. So again, this is, sorry, I interchange these in my head all the time, so I just don't think about the group numbers anymore. But this is the new group number. Now, what the old group number did is we didn't count across here like we're doing here. Instead, we counted it as A and B. So we would say like 1A, 2A, and then these were 1B through 10B. So we would say 3, 4, 5, 6, 7, and 8, and then A is underneath it. You don't have to worry about the A. It was just differentiating transition metals from the rest of the S block and P block. But the highest oxidation state element can have is that old group number. So like your noble gases can go up to a oxidation number of a +8. Halogens can be +7. Oxygen's family +6. Nitrogen's family +5. Carbon's family +4. Boron's family +3. Your alkaline metals, alkaline earth metals +2, and your alkali metals +1. That's the highest they could go. The lowest was that group number -8. So metals couldn't go negative, but that means this could go from 8 down to 0, 7 to -1, 6 to -2, 5 to -3, and 4 to -4. With that in mind, pull out a periodic table and look at it. Let's think about chlorine. Chlorine is a halogen. So now it's group 17. But its old group number was group 7, which means the highest it can have for an oxidation number is +7. The lowest it can have is that old group number. So again, if you ever want to get to the old group number, you just look at the current group number and subtract the number 10 for anything past the transition metals. Um, for your, when we're looking at your P block is really where we care here. But it's that, it's this Number 7, -8, it can go down to a -1 charge, which is what halogens want. They want to be a -1. So it can go as positive as +7, as negative as -1. But if I look at magnesium, magnesium is group 2. It's an alkaline earth metal, which means it can go +2, but the lowest it can go is down to 0 because it is a metal, and metals can't go negative. Why do we care? Because again, we want to look at redox reactions. A redox reaction is a reaction in which oxidation and reduction occur. And if one occurs, the other has to occur as well. They can't happen without the other happening. They are linked to each other. Conservation of mass. We cannot create nor destroy things. If one species is gaining electrons, they had to come from a different species. If one species is losing electrons, they had to come from somewhere. So reactions in which oxidation and reduction occur are called redox reactions. Redox for reduction and oxidation, or oxidation reduction reactions. Because again, oxidation cannot occur without reduction. One substance cannot be oxidized unless another substance is reduced. The easiest way to approach redox reactions is to determine the number, that oxidation state number you have, or your oxidation number of every element in the reaction, and then think about what's changing. So we told you that oxidation is losing electrons, and that is correct. That is absolutely 100% the fundamental definition. But a more useful definition of oxidation is an increase in oxidation number or state. Previously, I told you the definition of redox or reduction was gaining electrons, 100% valid, always true. More useful definition is a decrease in the oxidation number. So increase means more positive, decrease means more negative compared to where it started. Again, remember your oxidizing agent is a substance that's reduced itself, it oxidizes something else. Your reducing agent is a substance that's oxidized, it reduces something else. It's like your real estate agents, they're not selling real estate to themselves, they're selling it to someone else. So, in order to be an oxidizing agent, a substance must be in one of its higher oxidation numbers or higher oxidation states because it needs to be able to gain electrons. In order to be a reducing agent, a substance must contain an element in one of its lower oxidation states. It needs to be able to lose electrons to be able to reduce something else. There is a definition difference between general chemistry and organic chemistry, so I'm just right on the top of the slide over here. I want to emphasize that what I am telling you with the increase and decrease in number of electrons is the fundamental definition that is always true, no exceptions, okay? But organic, they look at it from a different perspective, which is totally fine. Oxidation versus reduction in Gen Chem versus OChem. And I only highlight this because students do get confused on it and they don't understand where it's coming from. Oxidation is a decrease in a number of electrons or increase in oxidation number. Reduction is the opposite. It's the increase in the number of electrons or decrease in your oxidation number. In organic, though, part of the reason it's called oxidation is because of oxygen. It's an increase in oxygen content. It increases the number of oxygen atoms in the species. It's a decrease in hydrogen in the species. And it still follows the fundamental definition of the change of electrons. It does. But if you have a species that you add more oxygen to, you've oxidized that species. If you have a species that you've decreased the oxygen content to, so the number of oxygens have decreased, you've reduced that species. You do that by increasing the hydrogen content in the species. Okay, let's talk through this example. Determine the oxidation number of each element in this reaction and then answer the following questions. First up, anything that's in its neutral phase 0. Magnesium solid, 0. H2 gas, 0. Those are easy to do. From there, I have to think about the species themselves and what they can do. HCl. The species listed second is going to take the negative charge. Truly, it's the species that's more electronegative, but we haven't learned electronegativity yet, so that's going to come in a future semester or future chapter this semester. But if it's a species listed second, that's the one that's going to take that negative charge, unless it's written in an organic way or something like that. But written as we're writing them here, it's a second species that will take the negative charge. Okay, just when you have something like hydrogen that could go positive or negative. Chlorine is a halogen and it's going to get its way. It wants to be a -1. Hydrogen can happily do that and form a +1. Magnesium chloride wants to be a -1. There are 2 of them. Magnesium wants to be +2. It's an alkaline earth metal, so when it forms a salt, when it forms a cation, it wants to lose those 2 electrons to form that salt. It's happy to do so. Now that I've determined the oxidation number of each element in this reaction, though, can I answer the questions below? Which element is oxidized? Well, oxidation is loss. So who lost electrons? I see magnesium went from a 0 state to a +2 state. That means that magnesium, metal, was oxidized. These questions are coming from the perspective of the reactants. It's the reactant that was oxidized. It's the reactant that was reduced. So which species is reduced? Well, reduction is gain. So who gained electrons? My H plus did. And this is where it gets a little tricky, but I want you to remember what this looks like in solution. What this actually looks like in solution, to start, I had some magnesium solid. HCl aqueous means I have H plus ions and Cl minus ions. So it's not HCl that's reduced, it's the H plus aqueous that's reduced because that's the species that was present in solution. Because again, I have the aqueous right there. What is the oxidizing agent? The oxidizing agent is reduced itself. It accepted the electrons. Who did that? That H plus did it. It accepted the electrons to form H2 gas. And who is the reducing agent? Well, this is oxidized. It donated or lost the electrons. So again, you're doing this from the perspective of the reactants. So it's the magnesium solid that's being reduced here, giving up its electrons for magnesium 2 plus ions. Because again, once these react, what's happening is the magnesium is giving up those electrons, forming Mg2 plus. And when it does it, it gives the electrons here, and this forms H2 gas. This is your spectator. Okay. Find the oxidation numbers of each element in the following compounds. CO2. The species listed second gets its preferred charge unless it literally can't do it, such as in peroxide. Oxygen wants to be a -2. There's 2 of them. So the carbon has to be +4 here. Lead 4 oxide. Notice the name there. Lead 4 oxide. Oxygen, -2. There's 2 of them, so lead has to be +4. The name told me the oxidation number. Chlorate, ClO3 minus. I do have that negative charge that I have to pay attention to here, okay? So my oxygens are each -2, but I have 3 of them. Overall, this has to equal to a -1 charge. So Cl minus 6 equals -1. The Cl has to be a +5 charge. And then again, hydrogen peroxide, we've just looked at this one, but I have it here again because I want to really emphasize hydrogens can only gain or lose 1, which means here the oxygen can only be a -1. It can't be a -2 as it prefers because my 2 hydrogen is 2 plus 1 plus my 2 oxygen at -1 each give me an overall charge of 0. And let's do our last three examples here. Determine the oxidizing agent and reducing agent in each reaction below. So I recommend, until you get comfortable doing these, to go through and assign oxidation numbers to every species in the reaction first. If I look at copper 2 chloride, notice what I did there is I purposely named it. Copper 2 means +2 charge on that copper. My aluminum is by itself, so it's got to be a 0. My copper is by itself, so it's a 0. And my aluminum chloride. Aluminum, always a +3 charge, and chloride here is going to be a -1. This is called a single displacement reaction. One species has been displaced. The aluminum went from a 0 charge to a +3, so it lost electrons, whereas the copper went from +2 to 0, so it gained electrons. That means my oxidizing agent is copper 2 plus because it was reduced. My reducing agent is aluminum, and aluminum solid if you want to be specific, because aluminum was oxidized. Fe2O3 reacts with CO to form Fe and CO2. So here, Fe2O3, this is iron 3 oxide, oxygen is -3, and the iron is oxygen is -2. There's 3 of them, giving an overall -6 charge. I have 2 iron, so each iron must be a +3 charge to charge balance this. Oxygen -2, carbon +2. Iron is down to 0. Oxygen -2, and carbon +4. So I see here my iron went from 3 to 0. So my iron gained electrons. My carbon went from +2 to +4. My carbon lost electrons. So lost electrons was carbon, not copper, carbon. Lost is oxidation, which means this is my reducing agent. Gained electrons was Fe3 plus. So this is my oxidizing agent. And the last one here, H plus, +1 charge. Oxygen -2, oxygen -2. Okay, manganese here, I have 4 oxygens at a -2 charge each, and overall the species has to be -1, which means the manganese here has to be a +7. My coppers here, I have 4 oxygen at -2 each, that's a -8, but the species needs a -2 charge, so the the 2 carbons have to add up to +6, which means each carbon must be a +3 charge. Manganese is by itself, +2. Oxygen is -2, so the hydrogen is +1. Oxygen is -2, the carbon is +4. Now I see what changes here. The hydrogen went from +1 to +1, so that didn't change at all. That's nice. The manganese went from +7 to +2. So something definitely happened there. That gained electrons. My oxygens all stayed at -2, and my copper went from +3 to +4. That lost electrons. Carbon. I keep saying copper. I mean carbon. I apologize. I do know my elements. For whatever reason, I just use copper more often, and so I tend to say that one more often. Lost electrons was carbon, so that is my reducing agent. Because it was oxidized. And gained electrons was my permanganate. Started off as a 7 plus charge. Truthfully, when you've got a non-metal like this, you're most likely going to say it like this. Okay, when it's a non-metal species, keep it together. When it's an ionic species, you can split them apart because how they split apart in solution. But here the manganese is probably going to be presented like this as your reducing agent. I mean, it says your oxidizing agent. So the permanganate here is your oxidizing agent. And that's because it is that in that entire species is a polyatomic, it is a molecule. So it's this entire species, this entire species. Whereas above, I had them split up a little bit, like because iron 3 oxide splits apart in solution, stuff like that. They split apart. So it's whatever species actually present that's going to dictate what the species is that's doing the oxidizing and reducing.